Hello, everyone. My name is Duncan from Amazon. Today, we're going to give a talk on a couple of aspects of things that we've been working on. For me, I spent a lot of time looking at Lustre recovery. I'm going to talk about a little bit about how Lustre recovery works, particularly in the cloud environment, some improvements that we've made, and then Zanhua will talk a little bit about some performance improvements that we've made recently. The first part of this talk is going to be talking about Lustre recovery. My main goal here, I think, is to get just an overall understanding of recovery. I think it's something that not everybody understands at a deeper level, and to establish a little bit of context. I'll talk a little bit about some of the particular challenges that you face, especially with regards to recovery in a cloud environment. And I'll talk about a particular case study that showed one of the limitations that recovery has in an environment like the cloud and how we improve it to make things more reliable. So one of the reasons that people really like products like FSx like Lustre is that FSx for Lustre is that you get to leverage all of the abilities that you have in the cloud. This includes things like scaling, flexibility, provisioning. You can mount it from your EKS clusters, your Spot instances, your EC2 instances, standalone auto-scaling group, and even on-premise with VPN connections. And this is really flexible. But it provides a couple of challenges as a cloud infrastructure provider, given that clients will appear and disappear all the time. One of the things that we've seen talked about in a number of the talks today and yesterday is that a lot of these workloads are using containers, they're using ephemeral instances. A lot of customers nowadays like to reboot their instances as a way of mitigation for errors. And so a lot of these things mean that you don't get clean unmounts, and that clients will be appearing and disappearing all the time. There's also some challenges that you face with supporting lots of different versions and architectures, even on the same file system. Today, we're going to mostly be focusing on that first issue. If you were to log in to your FSx account and look at one of the metrics that we provide, this might be a graph that you see. You can see that the client connections are changing by hundreds of clients per minute. This is very usual for many of these sort of ephemeral workloads. And just as a taste of what we'll talk about later, I'll show you this graph. Given the context, you may already understand what might be interesting about this. But first, I'm going to give a brief overview of the recovery process. So recovery is the process that Lustre uses to bring a target back online. This happens either when a server restarts or it fails over. And this could happen for any number of reasons, right? You need to patch, you need to upgrade, mitigating some kind of hardware issue, or some kind of kernel panic. The way that you should think of recovery is that you're rebuilding all of the state that you had from the prior server, using the information available in the clients and, as necessary, the other servers. The goal is to complete any of the in-flight RPCs through a process called replay, as well as grant any of the LDLM locks that are used for ongoing work. DNE and MDTs in particular, or MDTs and DNE in particular, are a little bit more complicated in the recovery process, which is a theme through most aspects of recovery. And they also have the job of completing the in-flight transactions, which are tracked by the update logs. I've broken recovery down into a couple of phases that I like to think about it in. This first phase isn't technically part of recovery, since it's not on the target recovery thread, but it's good context to keep in mind, given that it's important before the recovery starts. When a server comes back online or has failed over, you go through the normal setup process where you'll read the local logs and the config log from the MGS and register and start the proxy. The two of the things that we care about for recovery are these last received and replied data, which is used for the replay process. So I've got a couple of just visual diagrams of these processes. This first phase is fairly straightforward. Until it's ready for recovery, clients won't be able to reconnect. Once we have that information, we can move on to the client reconnection phase. There's two ways that clients might reconnect to a server. One, the sort of more normal way, is going to be the normal retry process, that once the client loses connection to a server that goes down, it will be reattempting the connection with backoff. And when it successfully reestablishes the connection, it will see that the server is in a recovering state and enter the client portion of recovery process. There's also a feature called imperative recovery, which uses a sort of a clever locking technique on the table that maps server NIDs to their statuses. And it uses revoking of that lock to proactively inform the clients that they need to update the table, which tells them the server is back online. When a client reconnects to the server, there's two scenarios that a particular request might be in. The request may have arrived at the server and actually have been processed and committed already, but that reply may not have made it back to the client before the server went offline. Those requests are just immediately replayed since we already committed them, and all we need to do is inform the client that the request is complete. It also drops any cached LDLM locks, so when you finish a read and it's not contended, just to speed up the recovery process. Everything else is added to the replay queue in the order of their transaction numbers. This phase is complete once all of the clients that we connected to before, which is stored in these files on disk, have connected and they're finished replaying, queuing all of their replays. And then on D&E MDTs, the MDT also has to connect to each other MDT and sort of synchronize the update log state, which is a very similar process of determining whether it needs to be committed, whether already committed, or it needs to be replayed, just like anything else. So yeah, just a sort of diagram of this process. One thing you might notice is that we've got the sort of red client here. So if clients can't make it back during recovery, then the server will evict those clients to make sure that they don't have any dirty data that we aren't going to be able to replay in recovery, and then move on to the rest of recovery with the remaining clients. This second phase, and sort of the final phase of recovery, is the actual replay. And if you got all of your clients reconnected, this is going to be a very simple process. You'll just replay everything in transaction order. Since you know that you've reconnected to everything that you need to, and everything will have been in order, you know there's no chance of a bad state if you just replay things in order, and it's fairly straightforward. If you needed to evict any of their clients, as we mentioned in the last slide, then there's a feature called version-based recovery, and effectively what this does is that the server will keep track of the object version that all requests operate on. And then when RPCs come in to operate on an object, they will include the version of the object they expect to operate on, and so recovery will only replay requests that have a matching object version. And this effectively means that if you have operations which don't depend on each other, such as you create a directory and then another client creates a sub file in that directory, if they don't depend on each other, then the object versions will match and they can replay regardless of transaction dependency. And this usually allows pretty much all of your clients to recover successfully as long as they were able to rejoin recovery. So that's great, but there's always problems. And in the event of problems, there's two numbers that control what recovery will do in sort of the unhappy path. The first is the soft timeout. By default, this is 5 minutes. If imperative recovery is enabled, which happens when the MGS is online and has been online for some minimum threshold, currently I think it's 5 minutes, then this will be cut in half. There's a second timeout, which is the hard timeout, which defaults to 15 minutes. And the soft timeout mostly represents how long the server will wait for clients to rejoin recovery. It effectively determines the starting timeout that the server has ticking, and that might get extended at some point, which we'll talk about in a second. If you have the soft timeout, like I said, you'll evict some of the clients. Some of the transactions may not be able to be replayed in VBR, but for a lot of workloads, you can recover pretty much everybody that rejoined recovery entirely. The hard timeout is where things become a problem. So if you hit the hard timeout, Lustre decides that recovery is going to be over no matter what the state of anything is in, and any client that hasn't completely finished recovery, so anything that had queued replays or was missing or anything like that, will get evicted and the server will not attempt any additional replays. It flushes the entire queue and it resumes processing. This is very bad. So at Amazon, availability is one of our highest concerns, and part of that is that obviously 15 minutes is a very long time to wait for recovery. So just from that perspective, hard timeouts, not great to hit under any circumstance. We also, evictions are something that we really try to avoid. Sometimes with certain workloads, you might be okay with evictions, especially in these ephemeral workloads where you're just going to sort of retry everything. But especially in more traditional HPC workloads, a lot of times you really want to protect the applications interface with the storage at all costs. When you get evicted, if you had an in-flight operation, like a read or a write, you will get an I/O error, and not every application will handle that properly. So we want to prevent that as much as we can. A consequence of this is that if we never were able to get into the VBR, you pretty much always evict most of your fleet. The only ones that will survive were effectively the ones that didn't need to recover anyway, because those were the ones that had already committed their transactions. They just hadn't heard back yet. It might be a little bit confusing to you, that third bullet, of why we would have hit this 15-minute hard timeout but not entered the VBR that you hit at the 5-minute timeout. And for that, I need to talk about one more thing, which is adaptive timeouts. So originally, Lustre used fixed timeouts, which were based on various values for everything. And then this concept of adaptive timeouts was introduced to dynamically extend the timeouts that Lustre would use when things were running slowly. So effectively, based on the actual observed latency of RPCs, the timeouts that Lustre will use will be extended to reflect the actual latency. And in a lot of situations, this is great. This allows you to have an under-provisioned server or sort of changing network topology or latency, and Lustre will handle it fine because it'll read sort of the time that things take and it will adjust the timeouts accordingly. The way that this interacts with recovery is that there's a portion of the adaptive timeout called service timeout, which is effectively the portion of adaptive timeout which is not in the network. The server uses this to estimate how long things take to actually process once they arrive at the server. Once the server reboots, this value needs to be recovered, and the way that it does this is that when a client reconnects and reconnects to the server, it will report what its adaptive timeout was before the server entered recovery. And the server will accept this service timeout from the client as the new value, and then go through this additional process of adding some time to that timeout. You've got 125 seconds worth of various things that are accounting for known processes that might impact recovery duration. So things like the network failover time, if you're doing that kind of thing, the time accounting for various kinds of retries, switching. So you sort of just add every value of those things which might happen, and an additional 25%, which in the code comment is described as an arbitrary minimum. We now have enough information to return to this graph that I showed earlier. So this was a particular case that we ran into which exposed one flaw of this adaptive timeout paradigm, which is that in these ephemeral workloads, where you have things coming online and offline all the time, this can affect recovery by breaking some of the assumptions here. So in this case, we had a fairly high intensity workload running on these ephemeral EC2 spot instances, and clients are mounting and disconnecting constantly. In this case, there were a lot of clients on a relatively small file system, and so the adaptive timeout was already getting fairly high. This is normal and expected, and it's actually one of the nice things that adaptive timeouts provides, is that this fairly under-provisioned file system was able to handle this workload, albeit slowing down. The problem, however, was that there was a hardware issue on the host, on the MDS, which slowed things down. And due to the hardware issues, the adaptive timeout continued to rise as requests continued to not be processed. The issue was detected, and the MDS was moved to new hardware. But as every other time during this entire workload, clients were being added and removed during the process, and some of the ephemeral instances went offline. When the MDS came back online, all of the existing clients rejoined recovery very quickly, because there was no network issue in this case. It was a hardware issue mitigated automatically. But they shared their adaptive timeout value of 600 seconds. We then go through the process that I described earlier, where we add 25% for that arbitrary minimum and the 125 for all of these known potential recovery cases, leading to a total recovery timeout value of 875 seconds. You might notice that's only 25 seconds short of the maximum hard timeout that recovery has, and 25 seconds was not long enough to replay all of these in-flight requests from these many clients because they had built up on being unable to process. After the 25 seconds, the recovery aborted and nearly the entire fleet was evicted. So what was the problem? The problem here fundamentally is that this adaptive timeout may be based on information which is no longer true. So if you think about the fact that the adaptive timeout was tracking the latency of RPC requests from a server that was previously running, when that server has moved to new hardware, that assumption that the adaptive timeouts are based on is no longer true. And so accepting this value caused the server to overestimate the time that it needed to perform various actions. This combined with the necessary fact that today, in recovery, you have to wait the full soft timeout for any clients to reconnect before moving on to the later phases. If clients are missing, you really need to be able to just evict them and move on. The rest of the clients should have no problem replaying their requests, and if the clients are gone, there's really no point in waiting 15 minutes for them. Our fix for this problem was don't extend the recovery on Connect. The whole idea of the adaptive timeout was this sort of service timeout component, which represents the time that the server takes to process things, which is necessarily going to need to be rediscovered when a server comes back online. We've got this open ticket for it. The logic is a little bit more complicated if you're using the built-in failover mechanism, because clients actually have to time out their RPCs before they will attempt the failover, so you have to give them more time. But the fundamental issue here is the same, is that you don't want to wait 15 minutes just because some clients are actually offline. You really want to be waiting in recovery for the things which might actually return. The other thing I would mention here is that especially timeouts, every timeout in Lustre is part of a hierarchy of timeouts. And if you have timeouts in one layer, even if every part of the way that you formulated that timeout is perfectly reasonable and well-formed, it can have impacts on other layers. In this case, the sort of very reasonable way that adaptive timeouts work being interpreted for recovery caused recovery to time out in a way that was very problematic. In our case, we have very few hard timeouts before, but given their severity, this is something that we're always tracing down and trying to reduce. And this resulted in almost 10 times fewer hard timeouts, since this value was, for the reasons that we talked about before, this value is contributing to that problem. And then even in general, if you don't hit all the way to the hard timeout, this helps because you don't extend, even if it's 5 minutes to 6 minutes to 7 minutes, if there's clients missing and you're not going to come back, you don't want to wait for them. In the future, I think there's more work to be done here with recovery. This is not the only place in recovery that has some kind of complicated timeout logic, and I'm sure that we can simplify and streamline more of it. There's this open ticket, which has a lot of ideas about recovery, and I think that Amazon and the open source community will be working on making things faster and more reliable. And Andreas also talked earlier about some ideas that we have for recovery. So I think there's a lot more work that we can do here. And I will pass the talk off to Zanhua to talk about StatAhead, Exciter StatAhead.
Cool. Thank you, Duncan. Let's start with something easier than all those complicated timeout. So I'll talk about async extended attribute StatAhead. So this is a small performance improvement on trying to close a gap for commands like ls-l. So if you ever wondered why commands like ls-l is not fast enough, even if you enable the existing StatAhead method, then this is a talk for you. So first, what is StatAhead? So if you run ls-l on a very large directory, by the way, we do have use case that a directory has 1 million files under it, and we need to run ls-l on that directory. When you run that command, the Lustre client needs to issue RPCs to servers to get all those metadata back. And if these RPCs are issued in sequence without any optimizations, then these latencies will add up very quickly. So what StatAhead does is do stat ahead of time. So let's say you issue the same number of RPCs, but they'll be issued ahead of time. And so that by the time that the scanner, the ls-l command, really needs the attribute information, those attributes are already in the cache, and there's a cache hit. Yeah, just some implementation details. We also have AGL here, stands for async glimpse lock, meaning basically it means the Lustre client also needs to send RPCs to OSTs as well to fetch the file sizes. So what is not enough for the existing StatHam method is it doesn't fetch extended attribute. So modern distros for commands like ls-l also needs city next label, POSIX echo. Those are all extended attributes that are not prefetched. So even if with StatHat enabled, you still need to pay the synchronous extended attribute RPC cost per file. So here are some numbers using our quick test, 10K files under a directory. Not that many files, but it's already the effect is already shown here. Without StatHat is 12 seconds, but even if you enable StatHat, it's 11 seconds. Not an ideal improvement. So our changes is quite simple. We just made a change on top of this existing StatHat method. We piggyback on the AGL pipeline to add a new step to fetch the extended attribute from metadata servers. We tried upstream this implementation in this Jira ticket, LU 17239. And we did some performance benchmarks. The table is not that easy to read. TLDR, we achieve 5 to 20 times faster on all kinds of different workloads on different across all the distros. But two things didn't work. One was DU on large flat directories. So DU worked if the number of files is less than 10K, if I remember correctly, or 1 million, or maybe 10K. Larger than that, DU didn't work. This is because of sorting algorithm in GU and GNUlib that is source inodes. So it breaks some assumptions in Lustre StatHat, so that then StatHat didn't work for that case. So we also have a fix in GNUlib. And the second thing didn't work is LFS fine, because LFS fine use iocto. It bypassed the step VFS stat pass, and StatHat just didn't get enabled. So ongoing future work, as I mentioned previously, the extended attribute prefetch is implemented together with AGL, and then I just realized that AGL only works for regular files. It doesn't work for large a directory containing a large number of directories. So we would like to extend it to non-regular files, symlinks directories as well. And yeah, we'll try merging the patch. There's some other work to do, addressing the feedback, adding some tests. Yeah, so this is just a summary. The existing StatHat doesn't prefetch extended attribute, but if we do that, we can see a significant speed up, and yeah, some next ongoing and future work. Yeah, thank you. This is the talk from us. And
any questions for our speakers?
There's a question about the recovery stuff, imperative recovery.
Yeah.
So my understanding is imperative recovery gets disabled if you have co-located MGS, MDS. Have you looked into that anymore? Do you know why the logic behind the disablement, or have you tried experimenting with it?
You're saying that for the MDS that is co-located, it won't have imperative recovery?
I think it disables imperative recovery for that particular MDS, and maybe more widely. I don't recall, though.
Yeah, I mean, the fundamental issue there is that Lustre has a minimum, I think it's 5-minute sort of time that it requires the MGS to have like a consistent view of that table. And so if the MGS has not been online for 5 minutes, then none of the servers get to use imperative recovery. So when you have a co-located MDS, the problem is that both of them are going to come back online at the same time. And so it's not that the co-location has caused Lustre to specifically disable that MDS from recovering. It's that they'll be recovering together, so you haven't met that 5-minute threshold for the MGS to enable IR.
That makes sense. I do wonder if fault-tolerant MGS would make imperative recovery better
Yes, this
for this
is
case.
specifically in plans for the imperative recovery to be covered, with fault-tolerant MGS.
Yeah.
Yeah.
Yes. So I'm not sure about the ordering.
Well, no, but imperative recovery is going to be replicated. Imperative recovery is going to be replicated on all the MGS replicas as well.
Yeah.
But
Yeah, I mean, I was thinking we are moving on to the next question, and I wasn't sure who's next in line.
oh, okay, sorry.
I guess I'll go. So, have you considered? I don't know if your orchestration layer is actually aware of all those clients that disappear or not. If there's a good visibility, have you considered that we also have this feature called evict by need, and you could actually proactively tell the server that, hey, look, those clients are dead, so don't even wait for them. And that might fix your problems without even your changes, because if all your clients that are currently alive have reconnected, who cares about all those timeouts? You would start your next steps right away.
Yeah, it's possible. I mean, you can't always have that information because you can mount file systems from anywhere. Like even using FSX, like you can mount from on-premise, you can mount from different environments, and say in the container case, you might have multiple clients running on the same host, so you can't just index on whether the host is healthy, that kind of thing. So I don't think that we have enough strong visibility to say like, yes, definitely this client is not coming back, and so we shouldn't wait for it. Yeah.
I see. I was just thinking that if there's some central body that schedules those containers, it's probably the same body that's going to kill them, so there's like the central visibility. But if there are like multiple things like this, still might be a good practice to tell people that, hey, look, plug this service in and your experience would be much better.
Yeah, I mean, there's lots of things that you can tell customers to do to get more reliability and performance out of their file system. Part of my job is to make sure that the file system works for any customer, regardless of whether they have read through every best practice doc, right? So.
Okay, thank you.
Hey, were you next or? Okay. First of all, thanks for completely triggering me at the end of LUG. That's like such a problem for us, what you're describing, and even with all the blogs and all of the documentation, yes, spot instances blow up clients and they're gone, and we hit this exact thing. I think we already teased at what was essentially my question, which was, have you guys figured out like a good way? Like you said, if you know it's not going to come back, like I've considered, the VMs are unfortunately on the client side of the wall, but you might be able to like change the mount. If you could get the customer to mount in this way, or you could like give them packages that included it, a UUID that basically referenced the VM on which it was running, and then you could detect that on the MDT side or MGS side, you'd be able to do the evict by NID thing. And so that's been like in the back of my head of, because you really can't know otherwise. You don't know if you're just slow, if the thing has a network hiccup, and it's going to come back. So that, I love what you did. I just don't know right now how we can actually say with any confidence that it's not going to come back.
Yeah, I think it's a tricky problem. You could probably have things in the cloud environment. There's likely some way that you could do that. I can't say that we have any specific ideas right now. But there's also, I think, there's lots of things that will be applicable even not in a cloud environment. So we talked about if you have good measurement on recovery, you can use some threshold that isn't 100%. Especially, so the original VBR design included this idea of post-recovery replay. So you would go through this normal recovery process, and then if you went into VBR, you would finish recovery, but you wouldn't evict clients that hadn't made it back yet immediately. And once they reconnected, you could still use that object version matching paradigm to replay and recover them without getting an IO error. And so this also would help with the process of like, you could be more aggressive about leaving clients behind. Based on what I've heard, that original design just wasn't implemented due to like just time for development. So I think that work could be revived. And I'm sure there's lots of other places that we can look at improving recovery time.
Awesome. Thank you.
So I have a question about your X-adder head. Is that strictly tied to readdir?
I'm not sure. We have the implementer team sitting there.
Yeah, it's just keying off of what. So to trigger stat ahead, it's you do a bunch of readers, and then when you start statting them one by one, stat ahead thread will kick off, right? And the X-adder stuff is basically hooking on that exact same mechanism, so behavior is exactly the same. Andreas wants to say something.
I mean, without the read dir, you don't know what a head is, right? Because it's statting them in read dir order. And so it's not like you can just do it by hash number or something else. You can't predict the file names to stat ahead unless you have something to work, and that's in read dir order.
So for example, if we were navigating not through the namespace, but say through a sequence of FIDs, this would not be very helpful. Is that correct?
There was.
Statting in fig order would be kind of evil, right? Depends what you're doing, I guess.
Thank you.
There was some patches for more predictive stat ahead, so it was like depth first, breadth first. If you're doing like a find or something and statting everything while finding. So it's not impossible that you could extend stat ahead to do something more than just, you're going to stat everything linearly.
But it still starts with a read dir. If you just know the file names pattern and you just do like direct file name access, like we have no clue that, okay, this is a sequential access that works off of whatever directory access. And so like it really must start with read dir first before you could even apply all the smarts.
Since you're so interested in the timeouts, you know that even though there's a hierarchy, a lot of times that if you change one of the timeouts higher up in the hierarchy, the lower parts of the hierarchy are not like synchronized and adapted to those changes. So this is a known problem for a long time. So if you're interested in fixing this, we tried to do this for LNet, but I don't know even if that's 100% complete.
Yeah, I remember that Chris Huang gave a talk last year about this process. So yeah, I mean this is the particular timeout that I've been concerned with recently. But yeah, certainly I think there's more to do there.
Separate question about X-adder ahead. I think one of the flaws that we have is that on the Lustre, in the kernel side, we're trying to predict what LS is doing, right? And we can only guess so much. I think the real solution is to do something like make LS parallel, right? I mean, there's in the newer kernels, there's IOU ring, which you can actually use for metadata operations now, and it would be not impossible. I don't know that IOU ring works super well for Lustre yet on the metadata side. Definitely for the data side, it works fine. But it's conceivable that we could get like an event-driven, parallel IOU ring going in to LS, and there's a Rust, version of file utils or core utils that may be more amenable to, having sophisticated, patterns, like you're saying, the sort inode order ls, that was a hack essentially to try and guess what the underlying file system is doing. But if we could have 30 or 60 or whatever stats and getx adders and everything like that going in parallel, they can send them to multiple MDTs in parallel. You can do this event-driven loop based on read-dir pages coming back, right? I think that's the real way to get super fast performance, right, is break this serialized LS behavior in the first place.
Yeah, and I think there's even more potential if you have some kind of batching mechanism like IOU ring, right? Yeah. One thing that we've thought vaguely about in this process is you could, since with IOU ring you kind of have knowledge of the batch that is going to be needed to be processed, you could get a lock and hold it between operations if the lock is shared. So this helps with things like maybe you're LSing, you have clients that are like LSing a big directory and clients that are operating within that directory. If you have something that needs to create 30 files, it might be ping-ponging back and forth with the locks, with the protected write lock, protected read lock. And you could just grab that write lock with the IOU ring buffer, do all your writes, and then hand it off so you don't have so much ping-ponging, both get faster. Just a thought, not particularly related to exciter stat ahead.
There was, going back to the IOU ring in the Rust core utils, I had submitted a patch to the Rust core utils to parallelize ls-l. It just used something very simple, like Rayon or whatever. They were amenable to it. I didn't actually get that patch over the line because I think IOU ring probably would be better if they moved in that direction. I think it's just somebody needs to do the work, but I think they would happily accept it. And Lustre, there was a Jira filed at least for doing more automatic batching of, ideally if you submit a bunch of things via IOU ring, Lustre would be smart enough to say oh, these are a bunch of async requests to the same node and then jam those together in the same RPC or something.
Alrighty, any more questions for our speakers? Well, thank you all for your wonderful speech. Round of applause.